In the last video, Leon introduced the Newton-Cotes formulas for numerically solving integrals. Now he is wondering if there are any, maybe even more elegant, alternatives to these quadrature formulas. Frederick may have such an alternative. Let him introduce Gauss Quadrature to us. Just as for the Newton-Cotes formulas, the aim is to numerically solve an integral over an interval a,b. Also equal to the last video, we want to come up with a formula where the integral is approximated with a simple sum. Just like before, the sum may depend on some weights omega I and support points xi, where the support points must be distinct. This time, however, we allow the support points to be unevenly distributed, allowing for more degrees of freedom. In fact, it can be proven that the highest order, and therefore the accuracy, any quadrature formula can reach is 2n-1, compared to only order n for the Newton-Cotes formulas. Gauss Quadrature will reach this highest order. This derivation will be quite complex. Before we start, however, let us please remind you of liking the video and subscribing to the channel if you enjoy the content. It really is appreciated. As an example, we derived the Gauss Quadrature formula for a polynomial of degree 3. Therefore, the order of the scheme will also be 3. The derivation for higher or lower order is performed equivalently. So, our function f of x is given by the general polynomial of degree 3, with coefficients a0 to a3. Let's first consider the special case where we do not integrate over the general interval ab, but the special case interval -1 to 1. With these limitations, the area a of the function f of x can be calculated straightforwardly. We just integrate the general polynomial of order 3 over the given interval. The uneven coefficients a1 and a3 vanish due to the symmetry of the interval, and what remains is the area a equal to 2a0 plus 2/3 a2. We mark this equation as equation 1. Let's now consider the same integral using the quadrature formula. Remember that the order of a scheme corresponds to the highest degree polynomial that can be integrated exactly. The order of the Gauss quadrature is 2n-1, with n being the number of weights and support points. Since we want to integrate a function of order 3, n must be equal to 2 in order to integrate this function exactly. With this, we only need 2 support points and weights and can write a equals omega1 f of x1 plus omega2 f of x2. And here, as indicated by the red equal sign, the quadrature is not an approximation, since we know that the order of the scheme is high enough to integrate the polynomial exactly. Now, inserting our polynomial of degree 3 into these terms yields this lengthy equation. We mark this one as equation 2. The scheme can now be derived by equating equations 1 and 2. Consider equation 1 on the left hand side and equation 2 on the right hand side. Here, we assumed the terms containing the uneven constants a1 and a3 of equation 2 as being equal to 0. Note that the equation as it is still has 6 unknowns and we have only one equation. Hence, the solution will not be unique. We aim to solve this equation by comparing coefficients. More specifically, comparing the green and the blue parts of the equation. However, we suspect any valid different solution may also be a working quadrature formula, at least for polynomials of degree 3. Consider now the green parts. Cancelling the term a0 directly leaves us with one obvious solution. Omega1 equals omega2 equals 1. Now, let's investigate the blue parts. Cancelling a2 and inserting the omegas found in the previous step leaves us with this equation. This, again, can be solved by assuming the absolute values of x as being equal. Note here that the sign of x1 and x2 are opposites, otherwise x1 would be equal to x2, leaving us with only one support point, which is a contradiction to our initial assumption that there must be n, in our case 2, distinct support points. Note also that the weights and supports are in a sense symmetrical. For Gauss quadrature, the support points are symmetrically arranged around 0. And a similar symmetry holds for the weights, as we will see later. With this, we have all the weights and all the support points. We are finished. No, we are not finished, complains Leon. Watching Frederick's magic very closely, he determines that we only derive the special case integral over a symmetric interval -1 to 1. What about general intervals? Frederick replies that this interval is already the general case. Watch this. Consider the substitution t equals a plus b divided by 2 plus b minus a divided by 2 x. The resulting differential dt is equal to b minus a half times dx, with the interval being mapped from -1 to 1 to a, b. With this, we arrive at a general formula for the Gauss quadrature. A is approximated by b minus a half times the sum over the weights times the function evaluation at the points b plus a half plus b minus a half times xi, with xi and omega I being the same as calculated earlier. Let's now look at some lower order Gauss quadratures. For n equals 1, we find that x1 equals 0 and omega 1 equals 2. For n equals 2, we arrive at the familiar xi and omega I, and for n equals 3, with the resulting order of 5, we find the weights and support points as seen in the table. Note here the previously mentioned symmetry of the weights and support points. To wrap things up, Frederick names some advantages of the Gauss quadrature compared to the Newton-Cotes formulas. Namely that it is of higher order, more efficient since less function evaluations are involved, and it seems generally more elegant to him than the Newton-Cotes formulas. Leon, however, finds the drawback of the scheme that the support points have to be chosen as demanded by the scheme. If the function evaluations at these points are unknown, the expected high order cannot be guaranteed. If you managed to stick by until now, thank you very much for watching. We truly hope you enjoyed watching our content and hope to see you soon.